In this video, we introduce more properties of logarithms that will make your life easier, your answers cleaner, and you much more efficient at solving logarithmic and exponential equations. Let's get started. So to begin, I want to introduce a few properties that are going to make your life so much easier when we start solving these types of equations. The first property has to do with what we call condensing or expanding. So first thing to notice, if I choose to what we call condense two logarithms, there are a couple of criteria we have to have first. The first criteria is the logarithms have to have the same exact base. So that's criteria number one. Criteria number two is that the logarithms are being added or subtracted. So I see that here, addition, and I see subtraction. So you have logarithms with the same base that are being added or subtracted. But there's one more important criteria. Criteria number three. The logarithms have to have a coefficient of 1. So right now, do you notice that there's no number in front of each logarithm? It's kind of like if I have an x, it's implied to have a coefficient of 1. So you have to have a coefficient of 1 for each logarithm in order for this process to work. So with that in mind, let's take a look how it works. If I have a log base b plus another log base b, it turns out, and you can see this from some examples, but it turns out that the logarithm condenses, so it consolidates, into a single log with that same base. You have to copy that same base over. But now, if it's addition of the two logarithms, inside of the one argument, the single argument, I will have multiplication of my old arguments. So if the first argument was m and the second one was n, I am multiplying them together. So notice when I have addition of two logs, I will multiply inside the single logarithm with the same base. But again, those three criteria had to be satisfied. Same base, being added or subtracted, coefficients of 1. What do you think will happen when I subtract two logarithms with the same base and coefficients are 1? You are right if you said I'm going to divide. That is correct. This is log base b of m divided by n. So my first argument that was positive has m, and the logarithm which was negative had an argument of n. Okay, so the order matters here, just like it always does. Subtraction and division order matters, unlike addition and multiplication. So that's very important, and in this class, what we will be doing is just that. We will see logarithms with the same base, leading coefficient of 1, being added or subtracted, and we will condense them to a single logarithm. Now, when you go on, if you choose to go on to calculus, one of the things you'll do is you'll go the other direction. So instead of condensing, you will go in this direction, and that's what we call expanding. Why would you expand? Well, in calculus, you're going to see a funky symbol, maybe you've heard of it, called an integral. And you'll have something like logarithm base 5 of the square root of x plus 2 over 10 minus x. Something crazy like that. And I'll ask you to differentiate that between two numbers like 1 and 5. And you'll need to know what that means, and you'll learn what that means in calculus. But the first thing you're going to want to do in calculus is do algebra. And the algebra here would be to expand this single log into separate logarithms based on the fact that there's division in the argument. So if you notice the division in the argument, you would separate them into two logarithms which are being subtracted. So you would have log base 5 of the top part minus log base 5 of the bottom part. Then you could do your calculus problem. So the algebra you're learning now will be very beneficial to you in future math classes. Just a heads up. So for now, the main thing for us that we care about the condensing in algebra, but you need to know the expanding because that will be important in the future. Okay, another rule that is going to be super important for us in this class and in other classes is known as the power rule for logarithms. The power rule for logarithms says that if you have an exponent that you wish to bring down, which will be very important in our next video when we start solving exponential equations like 2 to the x equals 5. How would I solve for x? In order to bring down that power, we will need a logarithm. So that would be something to write down right now. Next class, we'll solve equations like this, 2 to the x equals 5. I can't do anything unless I can bring that power down. But the beautiful thing about this power rule, it says that I can take a logarithm of this side, and I can take a logarithm of the other side, base 10, base e, whatever base you like. And that would allow me to bring down my exponent as a coefficient. This would now become x times the log base 10 of 2 equals the log base 10 of 5. If you have a calculator right now that in front of you, you could undo the multiplication with division, and you would have that x equals log base 10 of 5, close the parenthesis, very important, divided by log base 10 of 2, and that would give you the answer for x. And you could now know the approximate and the exact. This is the exact answer, and the calculator gives you the approximate for the x value, which when you raise 2 to that power would give you 5. That's the only way we'll know how to solve this type of exponential equation, by using this power rule, which says if I have a log in front, I can bring a power down as the coefficient. So this becomes r times whatever that log is, base b of m. Very important rule. It also is important the other way. If you have a coefficient of a logarithm, remember how we said at the very beginning that if you're condensing, like we had above here, that you can't condense if you have a coefficient that's not a 1, right? So what if I had a 2 log here, right, at the beginning? I would first need to bring that 2 up as a power. Then I could condense. So it works both ways. If I have a power and there's a log in front, I can bring it in the front. But if I have a coefficient in front and I need to condense, I can bring it back up as the power. So it works both ways. Okay, one more thing to point out here that you may have noticed already. I don't know if you see the thing on the board right here, but log of 5 over log of 2, that's kind of clunky. It's kind of awkward to look at. And it turns out I could have rewritten this as log base 2 of 5. That's a lot prettier, and that's how most math textbooks would leave their answer. Why would they do that? Well, notice that if I were to switch that back to an exponential, this would say 2 to something equals 5. If I called the something x, I would have 2 to the x equals 5, wouldn't I? That's back to where I started. So that means the same thing. So what's the trick there? It's called the change of base formula. This is really helpful also if you were trying to put something like this into your calculator and you don't know how to necessarily put log base 2, because your calculator might just have log base 10, the LOG button, and log base E, the LN button. So what would you do? You would take a look at what happened here. The argument on the top became your argument, and the argument on the bottom became your base. So I like to think of A over B. So take a look at this definition here. If you have a logarithm base b of argument a, so I like to use a and b, that's the same thing as, let's get another color going on, the log, let's say base 10, so I won't need to write it, of argument a divided by the log base 10, let's say, of argument b. Now, did it have to be that I took the log of both sides in the question over here? No, I could have taken the natural log of both sides. This could have been the natural log of a over the natural log of b. It doesn't matter which base logarithm you pick, but since calculators recognize these two, I would recommend memorizing one or both of them. Okay? So if you have a log for any base a, you can put that in your calculator by using the change of base formula. And so that's what we're going to practice in a few moments. Okay, so make sure you have these in your notes very clearly. How do I condense? When can I condense? How do I expand? Why would I expand? How do I bring a power down? Oh, using a logarithm. How do I bring a coefficient up so that I can expand? Oh, using the power rule. And how do I input any logarithm base into my calculator? Using my change of base formula. Log of the argument over log of the base. Okay, let's take a look at applying these in our next slide. Example 1. It says, could you write as a sum or a difference of logarithms? In other words, a lot of plus and minus signs. They're asking you to expand, which is what we would be using this for in a calculus problem. So currently, it might be a little overwhelming with all of the radicals and parentheses. We have log base 3 of parentheses, the cube root of x, times parentheses, x squared minus 9, close parentheses. So we have a logarithm of a multiplication going on. So notice what I have here. I'll do this one with you, and maybe you can try the next one on your own. I have a product inside, don't I? When I touch, that means multiply. Juxtaposition in math is multiplication. So what I need to do is recognize, using my rules, feel free to use your notes, what does it mean if I want to expand into separate logarithms? What does it mean to have a product in my argument? That's right, it should become a sum of logarithms with the same base. So if you said I need to have log base 3 of something, plus, because a product inside the argument of a logarithm becomes a sum of those two logarithms, with the same base, log base 3 of something. If that's what you said, you're on the right track. Now let's be a little bit clever. Notice that radicals can be rewritten as something to a power that's a fractional power, rational exponents. So what is the cube root of x? Could I write that as x to some power? Yeah, it would be the 1/3 power. You might need to go back to a video or to some examples online or in your textbook. It's called rational exponents if you need help with that, okay? So the cube root of x is x to the 1/3. Okay, now I go to my second factor, if you will. So I have something times something, they're multiplied, those are called factors. X squared minus 9. Well, I could copy that right now. That's true. But what we want to look for when you're expanding is there any other product or quotient, meaning division, inside of arguments? If so, I need to separate. Also, are there any powers that I could bring in front? So you might have seen the power part first. 1/3 as a power could become the coefficient, couldn't it? I would now have 1/3, and that's how many copies I have of log base 3, can't forget the base that you're using, of plain old x, right? So that's the first term. The next term that we would have is a positive situation. And we notice now that this is really log base 3. But can I think of a factorization of x squared minus 9? Think back to your factoring expert days, right? What do I have here? Which pattern is this that can be factored? It starts with a D. It's 3 words. Difference of squares. Nice job. So this is x plus 3 times x minus 3. If you need to look that up, look up factoring, difference of squares, because x is squared and 3 is squared. Okay, do you see something that is helpful to us? Why did I factor there? Yeah, there's a product. Nice job. And a product, just like last time, becomes addition of logs with the same base. So this time we're going to split that up even further. So we're going to come on down and copy our new answer here. So now we have 1/3 log of x plus log of x plus 3, but I forgot the base. Be careful, don't be like your professor, got to keep the base, plus log base 3 of x minus 3. So we have to make sure we brought all the powers down and we factored as far as possible. This would be much easier to handle in calculus. Rather than taking an integral of this whole thing, we can take an integral of these bite-sized pieces. And that's the beauty of expanding in a calculus problem. For now, it can seem kind of painful because you might need to review some factoring, you might need to review some rational exponent rules. Try B on your own. Okay, so for B, what's going on here? That's right, we have a quotient inside. And what happens if I have a quotient inside there? I should take a sum or a difference of logarithms. If you said difference, you are correct. This should be a difference of 2 logarithms because it's a quotient inside the argument. So if you wrote log base 5 of the first argument minus log base 5 of the bottom argument, you'd be correct. But is there any factoring you could do? Ooh, we might need some more space. I'm going to make some room. See if you can do your factoring on your own if you haven't already. Okay, what factors did you get? Did you get x plus 2 and x plus 3 for the numerator? Check it out. 3 times 2 is 6, and 2x plus 3x is 5x. Yeah, that works. How about the denominator, 5x minus 10? Did that factor? Yeah, there's a greatest common factor. Good job, a GCF of 5. And if you factor out the GCF, you get x minus 2. So that's another thing we have to remember. If there's a GCF, that was always the easiest thing to factor. Now, do I have something else I could do then? If I have a product here and a product there? Now it's just like the problem above, isn't it? This product should become a sum of logarithms. So my first logarithm is still log base 5 of x plus 2. My second is log base 5 of x plus 3. Be really careful, though, when you have subtraction, like we have here, because subtraction affects everything to the right of it. So that subtraction sign, I'm going to put a big parentheses, or you can put brackets if you prefer. It should affect everything to the right of it. So let's split up our 2 logarithms here. We should have log base 5 of the first guy, 5. And then we should have plus log, because this is multiplication, so it's a sum, base 5 of x minus 2. Some students can do some of this in their head, right? They can remember that the sign will affect it and just make the log base 5 x minus 2 term negative to begin with. If you can do that in your head, awesome. But a lot of students need to write the parentheses out and show the distribution. So each of these should become negative. Well, there is one more thing you can do after you change those signs. So you have negative log base 5 of 5, and you have negative log base 5 of x minus 2. I'm going to erase the part I don't need and just write it out how it would end up looking. Okay, so let's get rid of the parentheses and let's distribute. This would become negative log base 5 of 5, and this would become a negative log base 5 of x minus 2. This is still base 5. Okay, with that in mind, the last thing you want to do is see if there's any terms you can combine that are exactly the same base and argument. You would combine them with adding their coefficients or subtracting appropriately, or if there's any simplification you can do. I see one simplification. Do you see anything that we learned in a previous video? That's right. If I have same base and the same argument, what does that become? If you said 1, you are correct, because 5 to the 1 equals 5. So this whole thing goes to 1. So if I lost anybody, that was this trick. I'll write it up here. Log base b of b is always equal to 1. So that thought bubble is how we just did that. Okay. So the last thing I look for, I do a quick survey. Is there any more simplification, any more factoring, any more powers, anything else I can do? No? Okay. Then these would be my 4 new terms that would be very helpful in a calculus problem. Okay, if that seemed painful, well, kind of get used to it. Math gets even more complicated, but it's much more powerful the more complicated it gets. Okay, so take a break if you need to before heading to the next example, because we're going to continue with more properties of logarithms. Here is another one. How would you rewrite into a single logarithm log base 2 of 1 over x plus log base 2 of 1 over x squared? Well, I notice I have the same base. Do you? Yeah, base 2. I also notice that their coefficients are both 1, and I'm adding them together. So how do I do that? Good job. You multiply in the argument. So log base 2 of something times something. But what were my original arguments? 1 over x is correct, and 1 over x squared. So what would this become if I multiplied those arguments together? Make sure you remember how to multiply your fractions here. What would I get there? 1 times 1 is 1 for the numerator. X times x squared is x cubed. If you were thinking something would cancel, you might have been thinking incorrectly that 1 was in the numerator and 1 was in the denominator, but that wasn't our case here, was it? They were both in the denominator, so they just multiplied together. Okay, so we have log base 2 of 1 over x cubed. Now that is going to be more helpful in our problems in algebra. In algebra, we're going to be solving equations involving multiple logarithms. So the first thing is condense and then apply one of the techniques we've taught you. Let's have you do B on your own. Okay, so in B, first thing I notice is I have subtraction of 2 logarithms with the same base. They're both base 10. Good job. Can I condense the way it is right now? No, because remember the coefficients have to both be a 1. So how could I make that 2 go away? The power rule. Good job. The power rule said if you have a coefficient of a logarithm, it can come back up as the power of the argument. The coefficient of a logarithm can come back up as the power of a logarithm. So this would now become negative log base 10 of x plus 1 squared. Cool. What else do I notice? Good. I noticed that this can be factored, couldn't it? So this is equal to log base 10 of what times what? Which two factors do I have here? For x squared plus 3x plus 2. If you said x plus 2 and x plus 1, that is correct, because 2 times 1 is 2 and 2x plus 1x is 3x. Okay, so here is where we're at. We are trying to condense. Is it possible to condense these now? Can I condense these now? Well, yes, because now I notice that I have 2 logarithms with the same base, coefficients are 1, and they're being subtracted. Condensing is now possible. So this condenses, go ahead and pause it if you need to now, see if you get the same result as me. Log base 10 of, how do I condense subtraction? That's right, with a giant quotient. So it's not multiplication now, but it is division. So the numerator would be x plus 2, x plus 1. What would the denominator be if I spelled it out for my reader? Instead of x plus 1 squared, I could write x plus 1, x plus 1. Why do you think that's more helpful to my reader? Well, that's right, because they can see that it cancels, doesn't it? Death to you, death to you. X plus 1 cancel, leaving me with my final answer of log base 10 of x plus 2 over x plus 1. If you got that far, I would be thrilled. But one mistake students sometimes make is they really want to cancel these x's and tell me the answer is 2 inside. Why can I not do that? Oh, that's right, because of addition, right? I can only cancel through multiplication. If it was 2 times x over 1 times x, then sure, cancel away. But with addition and subtraction in between terms, I cannot cancel through that. Okay, so this would be my final answer, and now I could solve an equation involving logarithms like this. All right, we have one more example. Let's head over to it. This one involves the change of base formula. It says, can you use that formula along with your calculator to evaluate the approximate answer? The first one says log base 5 of 18. So you have your calculator out, you look at it, and most likely, especially if it's a scientific calculator, you only have the log button, which is base 10, and the ln button, which is base e. So you're thinking, how do I do this if you don't have a very fancy calculator, right? Well, the change of base formula said, let's write it out again, that if I have a log base b of argument a, I could rewrite that as log, so that's base 10, of a, close that parentheses, that's critical, over log, so base 10, of b. As long as you pick the same base on top and bottom, this should work. You could have also used natural log, which is base e, of a divided by natural log of b. Just close your parentheses each time. So if that's the change of base formula, see if you can apply that for yourself and get the approximate answer in your calculator. Let's see how you did. Here you should have written down for me, maybe you did log of 18, the argument first, over log of 5, the base. That would be the exact answer. They mean the same thing. Now in your calculator, if you did it correctly by closing your parentheses, you should be getting 1.796 if I round it to the nearest thousandth, the nearest 3 decimals. Okay. Now, you can know that makes sense if you were to check yourself. In your calculator, you would say, does 5 to that answer give me 18? Does 5 to that answer give me 18? Your calculator should have an answer button. I think it's like second and plus, something like that on the graphing calculator. Scientifics are a little different. But you can enter 5 to that answer, and it should be roughly 18. If it's not, then you don't have the right answer. Okay. The next one is a little more interesting. It's saying 1/2 to what power would give me 15? Now think about what that would mean. If you multiply 1/2 by itself over and over again, shouldn't you be getting smaller? So what do you think is going to happen to get to 15? Yeah, you're going to have to multiply by the reciprocal of 1/2, aren't you? So that would mean a negative exponent. So we are expecting a negative answer. So to get this one, go ahead and try it yourself and then compare. Did you do natural log of 15 divided by the natural log of 0.5 or 1/2? If you close your parentheses correctly, your calculator should be giving you this negative answer, negative 3.907 if you round to the nearest thousandth or 3 decimal places. So what that would mean is if I took 1/2 and I raised it to this negative 3.907, I should be getting roughly 15. I say roughly because I've rounded it, right? If I hadn't rounded it here, if I did the exact answer, it would give me exactly 15. So the reason it had to have the negative exponent, it had to flip it to a 2 and then multiply 2 by itself that many times. That's kind of clever, isn't it? Okay, so we've talked about condensing, expanding, power rule, and change of base formula. I would recommend making flashcards until you know these rules. Then I would recommend practicing until you can't make a mistake, because you don't want to be an amateur, you want to be a professional. So practice, because math's not a spectator sport, and I'll see you next time.